हेलो।
या
आ रहा है।
मतलब आपको आ रहा है बट आई गेस स्ट्रीम में नहीं आ रहा। एक सेकंड। स्क्रीन शेयर करना।
हेलो। आ रहा है।
हाँ हाँ। अभिनव स्क्रीन शेयर करना। यप यू आर लाइव।
Should we start?
या लेट्स फर्स्ट शेयर इट ऑन द ग्रुप्स।
So, should we start? Hello.
यस वी शुड स्टार्ट नाउ।
Okay. So, hello everybody. Welcome to ANCC's lecture series on some important things that everyone must know to do well in competitive programming. So, this series will be split up into multiple tracks. The first track being centered around basic algorithms, C++ standard library, and some basic binary search and tree techniques that are very important in competitive programming. Um, I will be teaching you the first track, and in the next couple, we will have these lectures spread out over the next couple of weeks. Okay. So the one thing about CP that
Um,
um,
Hello, one
is
second.
quite
Is
yeah.
meeting link shared with everybody? One second, I'll just share the meeting link. I'll share both the G link and the YouTube link. Just give me 1 minute. Yeah, sorry. Yeah. Oh, okay. Sanket, just share. We'll share the Gmeet link as well, yeah, because say in between YouTube is not working properly, so they can check that as well.
या आई थिंक वी शुड शेयर द टीम
Huh.
लिंक।
Join it. Just 1 second. Uh, I think we can just wait for a couple of minutes and then like just and then we can start in a couple of minutes. I think yeah, people have started joining. Yeah, we'll just wait for a couple of minutes and we'll start at 8:35. Minutes and then like just yeah, we'll just wait for a couple of minutes and we'll start at 8:35.
How do I auto-admit people, or can I make someone else the admin?
Minutes and then like just yeah, we'll just wait for a couple of minutes and we'll start at 8:35.
How do I?
I think we can start now.
Okay.
और
So
वो
I-
जूस भी दे दो
yeah, yeah. Abhinav this side, and I'm from
ये
ANCC.
अच्छे से
And
चलेगा
over the next few weeks, ANCC will be taking a lot
चलेगा
of
ना
lectures covering important topics of competitive programming. Today we'll be starting with basics of the C++ standard template library and some important things that everyone must know before starting competitive programming. Today's session will be quite basic, but we'll cover quite important stuff. Please be attentive, and I hope you enjoy today's session. So, one thing about CP is that not all correct solutions pass. What I mean is that just because your solution gives a perfect answer doesn't mean that the judge will accept your solution. That is because of an error that you all might have already seen. It's the time limit exceeded error. So most modern judges allow us to perform about 10 power 8 atomic
अच्छा वो
operations
वाला
per
होता
second.
है ये वो कलर का होता है ऐसे कि उसका नाम भी यही होता है वो
That
उस
means
कलर का
that,
ब्लू कलर का होता है बाहर पूरा
can
ब्लू
you all hear
होता
me?
है
Hello?
उसका नाम यही होता है एक्सो ही होता है उसका ऑर्डर एक्सो
Someone's mic is
ये वाला
open.
हाँ ये वाली हाँ तो यही दे दो ये वाला अच्छा
I guess Abhinav, like you can mute him.
ये ले लेता हूँ
Yeah. So any solution that you write must obey the time limit conditions enforced by the problem. What that means is that, say you have a solution which involves some computation which takes more than this number of operations, then your solutions is bound to take much more time, and the judge will automatically reject solutions which take a lot of time. So let us consider this problem. So the problem is simple. It asks us to find the number of pairs of indices in a given list of numbers which sum up to this given target.
Abhinav, your screen is not
Screen
sharing.
Just a second. Yeah, so this is the problem. You are supposed to find number of pairs of indices such that they sum up to this value target. One simple way to solve this question would be iterating through each left index and each right index and see how many of them sum up to target. So let us actually count how many operations this would take. By operations, I mean operations which are not expensive to perform, such as this if statement or such as this increment. So this this for loop is executed once for I equal to 0. And for I equal to 0, this if statement is executed for j equal to 1, j equal to 2, and so on till j equal to n minus 1. Which means this increment and this or slash this block is executed n minus 1 times. Similarly, for I equal to 1, this would be executed from 2, 3, and so on till n minus 1, which is n minus 2 times. So we can compute that in total for this entire for loop, we would use n minus 1 plus n minus 2 plus n minus 3 and so on till 1, which all of us know is n into n minus 1 by 2. So say that we are given 10 power 5 numbers, our program ends up using about 10 power 10 operations, which would take about 100 seconds to run, and the judge automatically sees this and rejects your solution. To improve such things, such as finding solutions in much shorter time, we use a bunch of algorithms and data structures, and this is the thing that makes CP interesting. So I'll be covering the C++ standard library today. So C++ standard library is STL for short, and it gives us it lets us use a lot of predefined containers and algorithms that we do not have to write from scratch. The first container we are going to cover is called the vector. For those of you who come from a Python background, a vector is similar to a list in Python. So yeah. Yeah, a vector is similar to a list in Python. It is a list of variables or C++ objects that can have different lengths. So one way to initialize a vector is just you say vector int v of 10, 5. What this means is you have created a vector having 10 numbers with a default value 5. So yeah, so this is one way to initialize a vector. Another way to initialize a vector would be have an empty vector at first, and one by one add values to the vector. So the way you add values to a vector in C++ is v.pushback. So these two vectors are the exact same things. It has 10 copies of the value 5, and here we added the value 5 to the vector 10 times. Yeah, so one way to access elements from a vector, what we C++ provides a function saying v1 of 0. So there is something called an index in C++. What I mean by an index is v1 of 0 lets us access the first element of the list of the vector. And just like many other languages, vectors are indexed by 0 and not by 1. So v1 of 1 would be the second element, and so on. So if you would like to print this vector, all you would do is you would run a for loop from 0 to the size of vector and print v1 of I. Be careful here, because accessing something like v1 of 10, v1 of 10 would actually be the 11th element of v1, and the vector only has 10 elements. So accessing an element from a vector which doesn't exist usually gives something called a segmentation fault, and most online judges disqualify your solution if you have such segmentation faults. Yeah, so accessing elements or pushing elements back to a vector are not expensive operations. They happen almost instantly. So what I mean by that is, say the judge permits 10 power 8 operations per second, you might as well create a vector of size, say, 10 power 7, and um, input elements one by one. Is that clear? Okay. Yeah. So this is one way to print a vector. Another way that C++ provides is called range-based for loops. So the name is quite fancy, but the syntax is even simpler than this. Say you want to iterate the entire vector.
Your
What you can
screen
do
is
is,
not shared. Abhinav.
yeah, sorry. Yeah, so this is about range-based for loops. C++ provides a mechanism where you don't have to access each element one by one. You can instead say, for int element in this vector, just print this element. So these are two ways of doing equivalent things. Um, so one more way to do this would be for int and element in v1, cout element. The difference between these two things is that this loop, say you do some modification inside this, it does not affect the underlying vector. What this loop does is, one by one, it creates copies of each element and prints that, doubles it and prints it. But say you do element into equal to 2. What this does is it goes to the location of the v1 itself and updates an element in v1 and prints that. So here the elements of v1 are not doubled, are not changed, but here they are. Okay, so yeah, vectors also provide a lot of other operations. Say you want to know how many elements are in the vector, you just do v1 dot size. This is similar to len of v1 in Python. Okay. Yeah, vector also provides an operation called pop back. Just because you add an element in a vector doesn't mean that an element must be permanently there. You can remove the last element of the vector by doing pop back. And just like pushback, this is also a very inexpensive operation. Um, okay, so a vector also provides a method called insert. Okay, so before we look at the insert operation, I'll teach you what iterators are. So an iterator is basically a pointer to an element inside a vector. It is effectively a memory address. So what that means is that, say I want the address of the start of the vector, I can just say vector int iterator, it is v1 dot begin, and say I want to do the same printing again. What I can do is, while the iterator is not the end of a vector, print what the iterator has. Okay, and increment the iterator. So basically what this does is, it goes to the first location of the vector, prints what it contains, and then increments the iterator. So in the first run, it will print the first element. In the second run, it will print the second element, and so on until it becomes v1 dot end. So v1 dot end is not actually the last element of the vector. v1 dot end signifies one memory address after the end of vector. Okay. And if you don't understand anything, please feel free to stop me and clarify in case of any doubts. So what happens is, say it has finished printing the last element, IT gets incremented, and this check becomes equal and it just breaks. So yeah, coming back to the insert operation, the insert operation is provides a method to insert elements into the vector in any place you want. So the pushback operation allows us to push only at the end. The pop back operation also allows us to pop back from only the end. But the insert operation, if you give the address, if you give the iterator corresponding to where you want to insert and the value that you want to insert, you can just insert 10 at the beginning of the array. Say you want to insert two places after the beginning of the array, you could just do b1.begin plus 2, comma 10. So what this would do is it would increment this iterator twice, which signifies the third position, and before the third position, it's just going to insert 10. However, this is a word of caution for all of you. Just because there is just one command being executed does not mean that this operation is very cheap. What I mean is that in order to insert 10 at the beginning of the array, what C++ internally must do is that it sends the first element to the second position and the second position to the third position, second element to the third position, and so on. So just to accommodate one element at the end, the compiler, the program must send each of these elements
Your
one ahead
screen, Abhinav,
just to make space for this 10.
screen is not visible.
Yeah, is it better now? Okay. So till where was it cut? Hello.
Till first
Did
to
all of you
second.
understand the operation? Okay. So you all of you understood the insert program, insert operation, and why it is expensive. Hello.
Yeah, yeah.
Okay.
Yeah, can you also increase your font size a bit? Little bit?
Yeah. Okay. So just like the insert operation, C++ also provides a sort operation. So what I mean by that is, say you have your elements in a random jumbled order, say 3, 1, 4, 6, 9. Say vector int v1 equal to 3, 1, 4, 6, 9. Okay, this is another way of initializing a vector. You don't have to initialize all of them at same value. You don't have to push them back one by one. If you already know what the vector is, this is one more way you can initialize it. So say you want to sort this. C++ does not provide something like v1.sort. Instead, it provides something way cooler. You can do sort from the first element to the last element. So you provide iterators to the beginning of where you want to sort and to one after the end of where you want to sort. So if you print v1, this would just print the elements of v1 in a sorted order. Okay, so the vector is quite useful. However, it is quite useful. It is the container that we use almost all the time because it is easy to use and it allows us to access any element. Allows us to access any element of the array at any time quite cheaply. But one drawback is that, say you want to insert elements in the middle of the vector, or say you want to erase something in the middle of the vector, it is expensive to insert stuff in between. So say you want a container where you always want to maintain a sorted height order, say a sorted height order of children, and say some new child gets added to a school of height 7. So if you want to maintain this sorted order in a vector, what you would do is v1.insert at the third position. this guy of height 7. Sorry, at the 4th position. Yeah. Some person of height 7. However, this is quite expensive because, as I mentioned, it would involve shifting each element that is to the right by 1 position. So in worst case, this ends up using n operations instead of just 1. And remember, I told you that most online judges allow us to only run 10 power 8 operations per second. So what happens here is that, say you have a vector of length 10 power 5 and you insert 10 power 5 more elements somewhere in the middle, then you would have to perform 10 power 5 operations 10 power 5 times approximately, which would exceed the time limit. Which is why we have other data structures which STL provides, which allow us to do some operations such as insert quite in a much more efficient way. Okay, so before we move on to such advanced data structures, we'll see another data structure just like vector, that is pair. Okay, so yeah, semicolon. Yeah, so unlike vector, which allows us to store only elements of type int, or say only elements of type string, a pair also allows us to store elements of different type. But as the name suggests, you can only store 2 of them. So you can have a pair of int and string representing height of children. So heights of 0. Okay, sorry. Yeah. So say Abhinav has height 6 feet. You would store that as heights equal to Abhinav, sorry, 6 comma Abhinav. So this is a container which allows us to store 2 elements and only 2 elements of possibly different types. And say I want to print the elements of height. We do not do heights of 0 or heights of 1. Instead, since we have just 2
Your
elements, we just do
screen. Sorry. Abhinav, your screen is again
yeah,
gone.
yeah, yeah. Okay. So pairs allow us to access elements like this, such as heights dot first and heights dot second. As the name suggests, second gets you the element abhinav and first gets you the element 6. So the nice thing about STL is that you don't have to use these types alone. You can also have a vector of pairs. You can also have a vector of pair of pair. Yeah, and C++ allows composition of these types. And say you want to have many people like Abhinav in this vector, then you can do v3 dot pushback heights or v3 dot pushback heights again. And the way you would access is just like the way you would pair string. So you would access it just like you would do normally in a vector, such as v3 of 0 dot first and v3 of 0 dot second. Okay, so this is a basic introduction of 2 very oftenly used containers in STL, pairs and vectors. Okay, so let us come back to this problem. So say you want to optimize this. One way that we can think of, okay, let's move to a simple problem before jumping to this. That is, say you have a sorted list of numbers. Can you find out an efficient way to search for a given number in this vector without having to visit each of these individually? And the catch here is that each of these elements, this given list of numbers is sorted. So this is similar to what you would do while searching for an unknown word in a dictionary. You would say jump to the middle of the dictionary and check. Say I'm searching for cat. I would jump to the middle of dictionary and find jackfruit. So jackfruit is obviously comes over above cat. So I would search in the first half of the dictionary other than the second half. So I repeat by checking the first 25% and then say the second 30 and then the first 37.5%. And you know what, narrow down our search space so that we can find our element quite efficiently. So this is one visualization of the binary search algorithm. Say you're searching for the element 398 in this big list of numbers. What you can do is that this is the entire search space, and yeah, so you check the middle of the middle of the list. The middle is 416, which is bigger than 398. So you check in this space. The middle is 115, which is smaller than 398. So you check this, and then you check this, and then you check this, and then you finally find 398. So instead of having to visit each element one by one, we effectively divided each of these vectors into halves and searched a particular half instead of searching the entire array. So if we analyze how many accesses this would take, that would be, say there are n elements, we would need one extra access plus the number of accesses it would take to solve for half the array. So what we did here is that we have, say, 32 elements initially. We checked the 16th element. The 16th element was more. So at the expense of one access, we narrowed down our search space to only the first half of the array. So the number of operations you would take for a vector of n elements would be one more than the number of operations it would take for a vector of n by 2 elements. If we solve for a approximation of this, we can see that, so say you substitute n by 2 in place of n here, and say you substitute n by 4 in place of n here, we see that a sort of telescopic type series forms. Say you add, and then of course the base case being t of 0 equal to 0. You can add all of these equations, see that n by 2 and n by 2, this n by 2 and this n by 2 cancel out, this n by 4 and this n by 4 cancel out. So t of n is effectively the number of equations that we add, that we have, which is effectively log n. So how did I get log n here? In the first equation, I had n by 2 power 1. In the second equation, I have n by 2 square. Third equation, I have n by 2 cube. At the end, I would need log base 2 of n to make this n 0. So the number of operations that a binary search takes is effectively log base 2 of n. This is much better than our initial linear search. What we would do in this question would be iterate through each of these one by one, which would take n operations. Here we just
Screen.
Yeah, this is some Mac OS operating system issue, which I have for some reason. Okay. Yeah, so binary search takes log n operations compared to our basic linear search, which took n operations. So to make you visualize the difference between n and log n, say you have 10 power 6, n would be, we would take 10 to search in an array of 10 power 6 elements. We would have to go to each of these 10 power 6 elements one by one, and we would use 10 power 6 operations, compared to when, if it's log base 2 of n, we would use something like 20 operations, which is way, way better than 10 power 6. So this is the algorithm of binary search. The way we can use it to solve this problem is that let us see how we can optimize this. Okay, so we see that this, so say this given vector v is sorted. Yeah, one thing to keep note of is you can only apply binary search when the given vector has some sort of sorted order, or you can sort the given vector to have a nice order. And yeah, so say the given vector v is sorted, what we can do is we can iterate for the first element, and then instead of performing this entire big laborious linear search, instead we can binary search in the range I plus 1 to n minus 1 to search for the complement of v of I. The complement of v of I means the target minus v of I. So if my binary search returns a successful search for this number, we can say that we have found a number at I and a number in the range I plus 1 to n minus 1 that is equal to our target minus v of I. So this is an equivalent solution to this problem. And one very nice thing about STL is that you do not have to implement binary search by hand each time. If you know that your vector is sorted, what you can do is you can call C++ lower bound function. So what lower bound does is that it gives, so yeah, if you have the starting and ending iterators, given starting and ending iterators, so C++ under the hood performs a binary search for you. And if you also give it a value x, C++ returns an iterator, corresponding to the first number in V1, which is greater than equal to x. Is that clear? Okay. Right. So how we would use that here is that the first our search space is begin search would be v1.begin plus I plus 1, and we would have to search till the end of the array, which is v1.end. Okay, okay, this should be a vector. Yeah. So the functions that I mentioned do not work on arrays. They are exclusive for the vector class which HTL provides. And what we can do here is to search for target minus b of I. So we can have an int search for as target minus b of I. And okay, what we do is we search for the first element in V1 which is greater than equal to x, and just check if the element that C++ returned is the same as the x we were searching for. So say we had 1, 3, 6, 9, 10. 1, 3, 5, 6, 9, 10. So say we are searching for 4. What C++ would do is it would return an iterator corresponding to 5. And all we have to do from now is check if 4 and 5 are equal, which are not. So we conclude that 4 is not present in the array. So what we do here is auto IT is lower underscore bound, begin search, end search, search for. Right. So okay, say there is no number in V1 which is greater than equal to x. Then we would get the iterator. Yeah. Then C++ would return v1.end, not the last element. So we need to exclusively check. Say I'm searching for 12 in this array. Then C++ would return v1.end, and we can conclude that this does not exist. So we just put a check here. If it is v1.end, continue. There are no solutions here. Else, what we can do is just check if the value that IT contains is the same as the value you're searching for. This means that we found a complement, and we increment our counter. Say we wanted to find the number of such solutions. This works for arrays containing only distinct elements. Say the array contained repeated elements. What we could do is, so one solution is obviously to iterate through element just after this IT and check how many of them are equal. But a better solution is okay. Say the element. So the above solution works for vectors of distinct elements. But what if we have repeated elements? So what we want is that we want the first element which is equal to IT, and we also want the first element which is greater than IT. So we want, so the last element we are searching for would be, the element before the first element greater than search for, and the first element we are searching for would be the element which lower bound returns. So yeah, say that instead of 1, 3, 5, 6, 7, 9, 10, there are 1, 3, 5, 5, 6, 7, 10, and we are searching for target 8. what happens is, say the I is 1. We are searching for 8 minus 3, which is 5. We would try somehow to get the first and the last occurrences of 5, and then just subtract their positions to find out how many matches there are. So one nice thing about C++ is that not only does it give a lower bound function, it also gives an upper bound function. The names are a bit misleading here, but the only difference that between lower bound and upper bound is that instead of returning the first element greater than equal to, upper bound returns the first element which is greater than. Yeah. So this would be, this would be the first element greater than search for. And as always, you have to do this check again. Right. So if IT1 is equal to okay, so how do we count this? What we would do is, if we know that if we know where the first element greater than x is, and we know where the first element greater than equal to x is, just subtracting their positions would give us the count of x. And if IT1 is equal to v dot end, we know that no element is greater than x, so we add to the count the position of so we add v dot end minus it. Okay, so let us take an example. Say our target was 15, yeah, and say we are at 5. We would search for 10 in this half of the array. IT would just give the position of 10, but IT1 would give v dot end. So so what we do in this case when it gives v dot end is just see how many places v dot end is far away from this 10, which is one place. As I told earlier, that v dot end is 1 after the last element. So yeah, and else what we do is, say we are searching for a smaller value, say 10. Say we are searching for 11. Say we're searching for 11. What would happen is, say we are at I equal to I such that v of I is 5. Then we search for 11 minus 5, which is 6. Lower bound would return 6. Lower bound would return the iterator corresponding to 6, and upper bound would return the iterator corresponding to 7. And we just subtract IT1 and IT. So we, at the end, count is the number of pairs ij such that I less than j, and v of I plus v of j is target. So the number of iterations that we have used here is not n square, not n into n minus 1 by 2, but it is actually inside the for loop. We are using only about log n iterations, some multiple of log n iterations. So overall, we use about, say, 10n log n operations, which is way below 1e8. Right. So that completes our section on vectors and sorting and searching in a vector. So one thing you would have observed about sorting is that by default, C++ sorts in an ascending order. What we can do in C++ is also give custom ways to sort the vector. Is my screen visible? Right. Hello. Okay. So say we have a vector, then sorting would just sort this in an ascending order. But say we wanted to sort this in a descending order. What we can do is we can have a custom comparator for this. So the way we do that is v1.begin, v1.end. So C++ gives a greater int function which tells it to sort in a descending order. But say you had some a vector of pairs, then it would be difficult to find default comparators for each way of sorting. So say v1 is equal to, yeah, say our policy would be sort by the first element. If there is a tie, then please sort by the descending order of the second element. Then we would have no choice but to write our own comparison function. And the way to do that would be to write your own comparison function. And yeah, so this is the syntax to do so. You just write the comparison function between P1 and P2, and then you define your policy. That is, if they're equal, okay, the comparison function must return true if P1 should come before P2 in a sorted order. Right. So what we need here is that according to our policy, that we must sort by the first element. In case of ties, sort by descending order of second element. So there is a tie here, that is the first elements are equal. So I would have to return false if P1 dot second is less than P2 dot second, because if we want 2 to come after 4, then yeah, then 2 less than 4 must, then our comparison between 3 4 1 2, if we want 3 4 to come before 1 2, then our comparison of 3 4 and 1 2 must return true. So what happens here is that, say we have the comparison between 3 4 and 3 2. In our policy we want that 3 4 comes before 3 2. So in case of ties, that is 3 equal to 3, we return true if 4 is greater than 2. So what we have done here is sort by the first element. In case of tie, sort by second element in decreasing order. Yeah, so you can have all sorts of comparison functions, but one thing you must keep in mind is that comparing an element with itself, that is comparing 3 4 with 3 4, must always return false. So this is something which C++ strictly enforces. In case you return true while comparing two equal elements, C++ throws a segmentation fault. Yeah, so in summary, the comparison element defines a custom comparator, which tells us true if we want the first element P1 to come before P2 in our sorted order. And we can just call this with our comparison function to sort the array. So if you would like me to print this, yeah. So this would sort by the first element, and in case of ties, sort by the second element in decreasing order. So this would give 3 4. Yeah, it would give 3 4 3 2 and 5 6. Okay. So vectors and pairs are a really nice STL container. It allows us to do a lot of things. But one thing that we discussed earlier is that inserting in the middle of the vector is quite difficult and expensive, because it involves shifting elements to the right by each element to the right by one place, which takes n operations instead of just one. To handle this, C++ has other data structures like sets, multisets, maps, and priority queues, which we will discuss right now. So a set is basically a sorted collection of distinct elements, most importantly. So say you have a bunch of elements in a set, we insert 5 3 5 1. Okay, so under the hood, what we can visualize is that S would just have a sorted collection of what elements are in it. Say even if you insert 5 twice, it would maintain the distinctness property, and the S would just be 135. Now, C++ does not implement a set just like it does a vector. So you cannot actually do S of 0 or S of 1 or access something in the middle randomly. Instead, what we have to do to access elements of the set is either be okay. So Yeah, the way we would the way we would access elements of the set is either through a range-based for loop like this, which C++ has implemented under the hood, and this just gives us a sorted order of elements that are in S. But yeah, as I said, S of 0, S of 1, S of 2 does not work. Another way we could print the elements in a set would be initialize an iterator to the beginning of a set. So although it does not permit random access, but um, sets allow us to increment and decrement iterators. So IT plus plus and Cout star IT would give us 3, and IT minus minus and Cout star IT would give us 1. Okay, so the nice thing about sets is that inserting elements in the middle, erasing elements on demand are not very expensive. So even if you have multiple insert operations, what happens is that elements are inserted in a set quite inexpensively, and it takes about log n operations per insertion. Um, yeah, let me just write that down. Inserting in a set takes big O of log n operations. Yeah, right. So the reason this log n comes up is because under the hood, C++ has a binary search tree, which we will not get into right now. But you could sort of imagine that instead of having to shift around elements one by one, we just find a perfect location to insert the element 3 inside a tree and just insert it there without having to shift any elements whatsoever. Yeah. So just like s.insert, we have s.erase. So there are two types of erase. Either you can erase by value or you can erase by an iterator. Say you want to erase the first element of the set, all we can do is s.erase, s.begin. And similarly, if you want to erase the value 3 from the set, you just do s.erase 3. Both of these operations are very inexpensive. It just takes big O of log n operations. And yeah, and now that you have a sorted order, one nice thing about sets is that just like you had lower or upper bound in C++, lower or upper bound in a vector, we can also have lower and upper bound in sets. So just like a vector, we have lower bound returns an iterator corresponding to the first element greater than equal to the element that we the value that we provide. So auto IT's s dot lower bound 4 would probably give us 5, the first element which is more than 4. You can imagine that this set data structure would be quite useful. Okay, one trivial case where I can imagine it could be quite useful is, say you have a vector and you want to find only the distinct values which are present in the vector. So the way you can print only the distinct values would be either you can insert values of vector inside a set one by one, or you could just do this cool thing, which is provide the start and ending iterators, just populate S1 with the values of V. So S1 would be 1, 3, 5, 6, 7, and 10. So this was printing distinct numbers in a vector. And say you have multiple queries in the middle. That is, while inserting S1, we also want to find out what is the first value greater than equal to 4 or first value greater than equal to 5. Then you can support like a lot of such queries. So you can support 10 power 5 inserts, 10 power 6 inserts, and 10 power 6 searches, as many as you want, and even deletions too, which you cannot really do in a vector. Yeah, but you might be thinking that sets are so good, why even use a vector? The key thing about sets is that you cannot really randomly access an element. You cannot access the middle element of a set randomly. You cannot access the fourth element randomly like this. If you really want to access, say, the fifth element, what you would do is you would initialize an iterator as at the beginning of the set, and 5 times we would increment IT and print the value that it contains. So as you can see, this clearly takes a lot of operations. accessing the fifth element is not just a single operation. It would involve iterating around 5 times. So this was it about sets. Um, I I have a lot of problems in mind which I would like to give you as homework. So the STL containers that I taught you are are really important to solve these problems. So it is important that you have a good understanding of these. So let's look at multisets now. So a multiset is just like a set, but unlike the restriction that it contains only distinct elements, multiset also allows you to have repeated elements. Allows us to have repeated elements. So one use case that you might think is that, say you have a collection where elements are added or deleted one by one, and you want to preserve duplicate copies of these elements. And then what happens is that in a set, even if you add 2 twice, multiple times, it gets stored only once. And if you erase even once, it gets deleted completely. And this is about a set, but in a multi-set, this changes the whole game. We can have multiple copies of 2. You can have a multi-set which is 1, 2, 2, 3, 4, 5, 5, and so on. And we can just do m.erase, m.find 2. So this would erase exactly 1 copy of 2. So yeah, multi-set functions are just like sets functions, such as insert, m.insert 5, m.erase, okay. So there is one crucial distinction I would like to make here. That is the difference between, okay, I've not taught you about find operation. So find is just like, yeah. So say phi exists in this multiset. What C++ does is it just gives you an iterator corresponding to phi. But if phi does not exist in this multiset, say the multiset was this, then it would just give you m dot. Right. So say we are searching for phi in a multiset that does not contain phi. What C++ does, it just returns m dot end if phi does not exist in m. If phi exists, it would just give an iterator corresponding to the first phi in the multiset. So m dot erase, m dot find phi would essentially remove one copy of phi from this multiset if it exists. And yeah, so while erasing elements from a multiset, it is important to to take care of the fact that it must be present in the multiset before erasing, else C++ does a lot of random behavior. So you must first confirm if phi exists in the multiset by doing m.find is not equal to m.end, and then erase one copy of phi from the multiset. So you might have seen me use. Yeah. So you might have seen me using s.erase 4 here. So say you use the same m.erase phi. So what C++ does is that it erases all the copies of phi from the multiset. However, m.erase, m.find phi erases just one copy of phi. So if you are solving a problem where the number of copies of each element matter, please use this and not this. And the operation that I mentioned, as operations such as insert, erase, lower bound, upper bound, are all big O of log n. What I mean is that to do one such in erase or insert operation, the C++ program uses about 20 operations instead of 1e5. Big O of log n operations for insert and erase, where n is the size of the multiset. So in a vector, inserting or erasing in the middle would involve 1e5 operations if 1e5 elements in the vector. But in sets or multisets, you can afford to do this erase or insert in a multiset multiple number of times because it takes just log n operations. So the reason log n is popping up everywhere is because it is using the same binary search algorithm that we discussed earlier. Yeah. So apart from insert, erase, find, of course, it has the lower bound and upper bound functions as we discussed. And you might be noticing that the syntax for lower bound and upper bound is different for sets and vectors. For vectors, we were supposed to give, where was that? Yeah. For vectors, we are supposed to give a beginning and an ending iterator to search for. But in a set or multi-set, we just search the entire multi-set by default. I do not think C++ allows us to search in like half a multi-set. But yeah, this is the syntax that we follow to search for elements within a multi-set. Okay. So the next data structure that we'll be looking is the map. A map is similar to a dictionary that you use in Python. So the way you initialize a map in C++ is you have a map of key comma value. So this stores a key map is a list of key value pairs. And yeah, the way you can add elements to a map is just to m of I equal to 10, m of 3 equal to 20. And so it is literally a map in a mathematical sense. It maps keys to values. And one use case that I can think of for maps is that, say you have a vector, say vector int v is 1, 3, 5, 6, 7, 10. Now say you want to count how many times each of these elements appears in a vector. The one easy way that you can do this is you can iterate through each element in a vector and just do map of x plus plus. And finally, you can say someone asks you for how many times, hey, how many times does 2 appear? You can just say m of 2. Returns the number of times 2 appears in the vector. Okay, so yeah. So access in a map are cost about login operations just like we have in a multi-set. So m of x costs us login operations where n is the size of. Okay, so say you want to print out all the values in the map. What you can do is you can use a similar range-based for loop for auto p and m. So auto is basically okay. I should not be using auto here. For each pair in the map, for each pair p in a map, print p dot first and p dot second. So this prints out all the key value pairs that are there in the map. So say you have a vector of 1e5 elements. What you can do is you can increment the frequency of each element one by one, and finally print this element has this frequency and yeah. So okay, so just like we have iterators for sets, multisets, vectors, we also have iterators for maps. So m.begin gives us the first value of a map, first key value pair of a map, and by default maps are sorted. So maps are ordered by their key in ascending order. So auto it is equal to m.begin would probably give you so auto it is equal to m.begin would give you the iterator corresponding to the first element of a map. So say you want to access the first element, what you can do is cout star of it dot first and star of it dot second. So these stars dot first dot second and so on are just syntax. You will get a hang of them in eventually. But yeah, I'm trying my best to cover all these syntax nuances. So what star it does is that, say you have an iterator to a value in a map, star it would just give you the pair of key values. So the type of star it is just a pair of int comma int. So you can do dot first and dot second to find out what the first two values of the map are. First value of a map are. Okay, so not just like you did lowers and upper bounds in multi-sets, you can also do lower bound and upper bound in a map. So m dot lower bound 4 would give you an iterator corresponding to the first key which is greater than equal to 4. And just like that, upper bound would give you the first key which is greater than 4. Okay. Yeah. So this is one way to iterate through a map. Another way you can think of to iterate through a map is, again, say you have an iterator map int, iterator it1 which is m.begin. Then while it1 is while we do not reach the end of the map, just print out the keys and key value pair of the iterator. Okay, so this is to print, and this is to do the same binary search which we did. Yeah, this is pretty much it about the map data structure which we use on a day-to-day basis. Yeah, maps are pretty good data structures, but then they have the same lacking capability. That is, you cannot easily get the say the fifth element of a map or the sixth element of the map. Although you can binary search for a key in a map, you cannot randomly access any element of the map at inexpensive costs. So say I want fourth element of the map, then I can't do it by just doing MP of 4, because this would give the value corresponding to the key 4 and not the fourth element of the map. Right. So I think, yeah. So this was about maps, and the next data structure we'll be looking at is stack. So yeah. So a stack is a pretty commonly used data structure, but then a vector does almost everything a stack can, but yeah. So a stack has two main, okay, let me just disable this. A stack has three main operations that are push, pop, and a top. So what stack does is that it follows a last in first out principle. I will tell you what this means. Say I initialize a stack. What you can do is one by one you can insert elements in a stack. So this is the same as vector pushback, but yeah, it has more meaning if you initialize a stack instead of vector. So in stacks you can't do s of 0 or s of 1. You can only access s dot top. So in some way you can say that a stack is a dumbed down version of a vector where operations are limited. So the reason we do this is, if you're using a stack, you have certain meaning to the problem that you're trying to solve, and we would try to respect the constraints that the problem suggests. So to give you an example of where we would use a stack is, say you have a sequence of brackets. Say you have this sequence of brackets. So you would like to see if each opening bracket has its own closing bracket. Does each opening bracket have a closing bracket? So in this case, a stack would be quite useful. So yeah, the algorithm that we would use for this is that for each opening bracket, do we have a closing bracket? So say we encounter a closing bracket. We search at the top, we search just before this. Oh, do we have a matching opening bracket? So we do. So we have found a match for this. I'm sorry, I don't have a pen, so I can't really explain what I mean by a matching bracket. Yeah, say you have a bracket sequence like this. So what we would say, we do not have something like explicit like a stack. Intuitively, what we would try to check is that, does the first closing bracket have a corresponding opening bracket? If yes, just match them and delete them. Does this closing bracket have a matching opening bracket? If yes, just delete both of them. Does this have a match? Just delete both of this. Does this have a match? Just delete both of this. At the end, is it empty? Yes. So therefore, this is a balanced sequence. So it would be hard to implement the process that I thought of in terms of bare strings. So what we use is a stack data structure for this purpose. What we do here is we initialize an empty stack. Each time we see an opening bracket, if the bracket that we have is an opening bracket, then push in this stack the opening bracket. And if it's a closing bracket, or S of I is this, or S of I is this. Yeah, if it's an opening bracket, we will store a container containing all these opening brackets. And if it's a closing bracket, we check if a match for this closing bracket exists in the string. So the way we do that is we don't have to iterate through the entire stack. We just check the last recently added element of the stack. So say we encounter this first one, we would see the last recently added element in this stack, st, which is this bracket. And we would check, is the type of st.top the same as, okay, so if if s of I is of type this, first of all, I must check if the stack is empty, if the stack is non-empty. If the stack is non-empty, only then we check if there's a corresponding matching type for this bracket. So if st is non-empty, we just check if st.top is this. If that is the case, we have matched these two brackets and we say a green flag. Just remove this last recently matched thing from our stack and continue iterating. Say there is a mismatch. Say instead of this, there was this square bracket. We would detect that corresponding to this flower closing bracket, we have a square opening bracket. In this case, we must print immediately that CAIC no, we found a mismatch, and exit the process. So we would do the same for each type of bracket. And of course, if there is no matching bracket of any type, we would end the process now itself. So say you would encounter this case where there are less number of opening brackets compared to closing brackets. So in this case, what would happen is that say it was this. So at the start, at I equal to 0, we have a closing flower bracket. So the closing flower bracket would not match with either of these. So this else gets executed. The closing flower bracket matches with this. And then we check, hey, is our stack empty? Our stack is indeed empty because at the start of the process, we have not inserted anything in the stack. So we did not have anything to match this flower bracket. And we just say CAIC, there is no matching bracket at all. And at the end, if each opening bracket that we inserted, as you see, we insert each opening bracket. If each opening bracket we inserted had a closing bracket, had its corresponding match, then we would pop each of these. Okay, sorry. Instead of st.pop, st.pop. Yeah. So what this means is that if we have a corresponding opening bracket for this closed bracket, we no longer need this opening bracket because we already matched it. We essentially perform a search for this previous square bracket. So what happens is, okay, let me just do a dry run for this algorithm. At the start, it is empty. And we insert at the stack, at the first element, this is an opening bracket, so insert this. The next one is also an opening bracket, so insert this. Yeah. Yeah. The next element is also an opening bracket, so we just push this. The next element is a flower bracket, so we push this. And the next element is a closing bracket. When it is a closing bracket, we do not push it into the stack. Instead, we check the top of the stack. Is it the matching type of this closing bracket? Yes. It is a matching type, so we do not end the process. We just pop it from the stack and continue. And then we perform the check for this, where we find out that this bracket does not match this bracket. So we found a mismatch and we report that this is a mismatch, please end the process. So this is the algorithm which we use for finding a matching bracket sequence. So sorry, a regular bracket, checking if a given bracket sequence is regular. That is, each closing bracket has its own match. Yeah, that's about it for stacks. So we have only three operations that stack provides, that is push, pop, and top. We also have queues which work in a similar way as stacks. The only difference being, in stacks we pop from the top of the stack. Instead, in queues we have a pop operation which pops from the front of the container. So it is just like a queue that you would see in a shopping mall. The first person that gets in the queue is the first one to leave. Unlike here, where the first person to enter the container is at the top of the stack, and when we call pop, the top of the stack is popped off. In a queue, what we would have is that, say we are pushing 1, then pushing 3, then pushing 5, and pushing 7. Pop would pop 1 and not 7 in a queue. So in C++, initializing a queue is quite similar to initializing a stack. Instead of stack char st, we would just do queue char st, queue char q. And that's about it for today's lecture. We have covered a lot of important things that the C++ standard library has to offer. And I have a set of homework problems for you, which you can try. So take a note of these. Try implementing all of these using what you have studied so far before our next lecture. I hope you grasped most of the stuff that I taught today, and looking forward to the next lecture. Yeah. Does anyone have any questions or clarifications which you would like to ask?